let's try to find the partial derivative of some function with respect to multiple independent variables using the chain rule. So if I have some w, which is defined in terms of y and x, but if I look at what these x and y variable, or what these variables are, it turns out they're functions of s and t. So we can use what we've developed to construct the methods of how to get the partials of this with respect to s. So effectively we want to figure out how w is changing as s is changing, how w is changing as t is changing. So to do that, let's go ahead and write out our formula so we know what we're looking to do. Call the partial of w with respect to s is the partial derivatives for its initial variables, x and y, and then we chain the partials that essentially perform like fractions and cancel, do that cross cancellation. Again, doesn't behave that way, but we're going to write it like that. And then the partial with respect to t is exactly the same setup. The only thing that changes is instead of putting a ds, we put a dt. So to do this, it turns out we don't actually have to find 8 different quantities because they're the same here and here. So 1, 2, 3, 4, 5, 6 quantities. So let's go ahead and start computing them. First, let's go ahead and get the partials with respect to x and y. The partial with respect to x is 0, negative 6xy. And the partial with respect to y is 3y squared minus 3x squared. And remember, we need to get this in terms of s and t. So that's negative 6 e to the s, e to the t. Or we could write that as negative 6 to the e to the s plus t by the nature of exponents. And then in this case, if we factor out a 3, then y squared is e to the 2t, and x squared is e to the 2s. So then that's 3, that doesn't combine. Sorry, I was trying to overthink this. So now we have these in terms of t, but let's go ahead and get those partials with respect to the these parameters here, s and t. So the partial of x with respect to s is e to the s. The partial of x with respect to t is actually 0 because there's no t here. The partial of y with respect to s is 0, and the partial of y with respect to t is e to the t. So that's convenient because that tells us when we plug in here and here, those are both going to be 0, so we don't have to really think that hard about it. Let's put that together. So I need the partial of w with respect to x times the partial of x with respect to s plus the partial of w with respect to y times 0. So that's negative 6 e to the 2s plus t. And then the partial with respect to t, take partial of w with respect to x, so negative 6 e to the s plus t, and then we multiply that times the partial of x with respect to t, which is 0, plus the partial with respect to y, and the partial of y with respect to t is e to the t. So now we get that. In doing so, we need to find the values at these points. So we need to find the partial with respect to s at the values of s and t are -1 and 2. So then it's -6 e to the 2 times -1 plus 2. So -6 e to the 0, which is just -6. And then the partial of w with respect to t, when s and t is equal to -1, 2, is 3e to the 3 times 2 minus 3e to the 2, -1 plus 2. So that's 3e to the 6 minus 3. So notice that these partials in these given directions evaluate, they not only are different functions, and they evaluate to having different values, which is something you might expect, that the change in different directions has different values.